Yes, you will bash your head against it and get nowhere, basically. Um, you're welcome. Okay, so one of the interesting things about the files, as usual, got zillion billion windows open because a zillion billion things are happening. I'm noticing not all of the images are coming into your directory. They are at the moment, and I'm not sure what happens with this name thing. And the air mass is a bit funny. I think there might be something going downhill at LCO. I'll get them to check it out. That's your new images for target 2, I think. Um, but what was I doing? Okay, going in here. So you have DAO. Okay, one interesting thing about DAO files. We'll open it up. And I showed you this last time. See how there's a comma there? If I get an Excel thing open, sorry. Okay, if I open one in Excel and I go delimited and go next, go comma, see how it replaces the commas with columns. Pretty easy, huh? So that's one of the benefits of having the commas in there. So now you've got an Excel file that has it all in there. Yeah, counts and error. Well, you can do a little plot of the whatever you like. As you get more counts, the error goes up, but as a fraction of the error. Oop. Anyway, I'm playing around. Oh yeah, this is signal to noise now. So yeah, so you can see that once you get up past 25,000 counts, it kind of plateaus a bit. Anyway, I'm just showing you can open it in Excel. Other way you can do it is, I'm not sure if you can open with. Can I open with Excel? Oh, it's already open. Let's try it again. Open with Excel. Ah, yeah. See, it comes open and it's got the columns there, so it thinks everything's. I saw something. I'm going off on a tangent here. Text to columns. I only saw this last night. This is not something I've known forever. I actually known it for 12 hours. Haha! So you can do it that way as well. Bing! So you can get it open in Excel, which makes Excel being very handy. Anyway, so back to here. Yes, so you can open it in text edit. The best editor I know of is Notepad++. It's good because if you're working in code and stuff, it will color things for you according to what they are, and there's a lot of nice stuff it does. Notepad++. Voila. That's what I use. Pretty sure you can get it from Mac and PC and whatever you like. Maybe it's just Windows. I like it anyway. Yeah, it must be just Windows. Anyway, that's my favorite one. But yep, okay. And then we actually, what's even more spantacular is we have some software. We're a bit far away yet from using it. But so if you put all your files in here, all your DAO files. So yeah, so there's 1,000 of them. 1,000 images in here. So imagine if you had kids and you do have kids. You have kids and students. Sorry, make myself laugh sometimes. If you have students and they'd have to go through here and find an individual star each and every time. Well, a lot of the time I picked the wrong star. But if you have 1,000 images, that's going to take a long time. So there's this software here that actually Matthew, the guy who did one of the posters you might have seen, just for interest. This guy, he wrote some software to do his project. See, so that he can look for all. He had about a couple of hundred images, so he could get his values out. So just need to empty this and empty that. Because this is where the results go. So I'm going to start this off and then describe Deofot and what it is, because the 1,000 files will take a little while. There's instructions in this software about how to use it on Mac, how to use it on Windows. But basically, certainly don't. Oops. I mean, this is just in a README file, so it really isn't that hard to do. Taking ages to load for some reason today. And then we import match, which is a program that Matthew wrote that matches. You make a CSV file, comma separated value file, and you put in your stars. So you have the comparison star and RLRA and 3 other stars which Sichuan was using as check stars. So what that does is we go match.run, and it will go through all of the files in test docs. So each of these flickering things is it going through test docs and picking out each of those stars from each of the DAO files. Yeah, so that's going to take a little while. So while it's doing that, let's have some what is Deofot. It's a story of intrigue. Okay, so you have aperture photometry. Ooh. Why is my computer slow today? What? So strange. Okay, have a star, and then we put an aperture around it. Ooh. Aperture around it, and then we count up all of the things, right? That's aperture photometry. But aperture photometry sort of assumes that the star is a circle. Sort of. There's a long story that involves things you don't have to know at the moment. But you know, circular aperture, circular star. But as you can see from, I probably still have your thing open from yesterday. You've got a donut star, and you've got a blob star, and a goop star, and a blur star. So your star is actually more like that, maybe. Well, most stars will be like that to some extent, much like all orbiters are ellipses, and you know, very special case is a circle. So if you put you can see a round circle around an ellipse. It's probably not the best choice. Also, when you put the circle around, we're also counting up all of the noise there. So you're counting up lots of noise. So you're adding noise into your image. We're counting up all of this stuff in the sky that's in the circle as well as the star. So if you're counting the center of the star, counting the values at the center of the star, so if you had an aperture, and then we'll put some noise down here, and then that's 0. So if you have an aperture that is this big, most of your measurement is signal and only a little bit is noise. Yeah. But if you start having a bigger aperture, and you have to have a bigger aperture to collect all of the light from the star, so you bring it out here, so you have an aperture that captures all of the star, you are capturing less and less signal as you go further out, and there's more and more pixels as you go further out. So if you think of how many pixels are in a circle, as you go further out, there's more and more. And so your signal to noise, you're adding more noise than signal at some certain point. There's a way to use aperture photometry where you do this measurement here, right, and just measure this and then extrapolate what the rest of it should look like if we assume that it's a circle. It's called, and you won't be using it, but it's called aperture corrections. So you have a much smaller aperture, that's usually of the order of the full width half maximum. So you'd probably have an aperture that's smaller than the image of the star, and then you kind of use a bit of math to correct to figure out how much flux you would have got. I'm not going to go into detail about that, but I know all about it. But what we're going to deal with Daofot, so aperture corrections is what aperture photometry tool allows you to do. Like aperture photometry tool looks more confusing, but it's much more powerful. It allows you to do this aperture corrections. It also allows much more sophisticated estimates of the sky background, so you make a much better aperture photometry measurement than AstroImage-J can. But even beyond that, so for bright stars, aperture photometry is great, and there's no benefit to it over PSF photometry. So PSF photometry is point spread function photometry. Basically what it does is, I'll just do it in 2D here. If you have a thing like that, this is a star, this image of the star is the same all over the image. So each star will have this profile, because the star is a point source of light, a small insignificant point of light, well, as far as the telescope is concerned, and it gets broadened by the atmosphere and the diffraction of the telescope and all sorts of stuff. But it means that each star in the image will have that same sort of shape. So if you look at all the stars in this image, they all, to a first approximation, all have the same blobby shape. Yeah. So, and that's not great for aperture photometry. Aperture photometry on this would work okay. But see how it's got this blurb out there? That's probably because the wind came along and blew the telescope, and the telescope shook, and then it kind of does that. So all of the stars have got the same blobby shape. So point spread function, well, point refers to the small bit of light in the sky. The spread is how the telescope in the atmosphere has spread the light out. The function, I guess that's just, this can be described as a function. Instead of putting a circle around the image and building it up and counting everything underneath it, what point spread function, and the function here is the key, is it models it. So first the software goes and looks at all the stars and gets the shape. So the first I'll just describe what Daofot does, otherwise I'll give you the whole history of the thing. So Daofot will go through and say, actually I'll make a blobby version. Okay, I'm going to make a blob Maybe it's skewed that way, and maybe it's got like a spike out there. Okay, so that's the start. So the first thing that Deifot will do is it will figure out a profile, I think, and the usual one is a Lorentz profile. That requires me to spectral line shape. Yeah, so a Lorentz profile is, it's a function. You don't have to know what it is. Voigt. It's just a bunch of functions that draw those things I draw all the time. Yeah, so a Gaussian is described as this thing, and a Lorentz is a different one. I think Deifot uses Lorentzian. You can actually set it to a bunch of different things. I think it's set to Lorentz. Where's your email going? So many things. Sorry. Let me get. Man, I've got to learn how to do less stuff. I'll just bring it out here. So Deifot will start by, getting that equation that draws the profile and fitting that to the star. So it will it can incorporate this skew into the function, right? So it will look at all the stars and get the shape of all the stars. Does that make sense? And if that function can incorporate skew in the sense that one side's, it's not symmetrical, it will incorporate some screw, but it has a smooth function. So that's step number one. Step number two in the world of Deifot is it gets that initial function, and then it creates a perturbation map. Whoop, whoop. Okay. And so it's got the smoothing varying function, which is a mathematical function, and it figures out the coefficients. Sorry, shouldn't have shut it. It figures out the coefficients for the function so that it fits. It fits whatever. I don't know what the functions are. I just tell it to use it. Look at that. You're not going to show that to a high school student. All you need to tell them is it fits something, and it's some math thing. So the perturbation is what's the difference for all the stars between that profile we made and the actual PSF. So it also models a bit of perturbation on top. So if we have some weird glitch out the side, we've got a weird glitch in this image here outside. It might be shown as they might do a profile across and incorporate that in. But anyway, it has this perturbation which it also kind of fits the shape of the star. So you can see so far we haven't talked about background or anything because you don't sort of need to. Once it has the shape of the star, and it does need to know the background. So say you have a star. Oh, I should just say that this is a 2D version, so I can draw it here. But it's actually, it's a 1D. Okay. It makes the point spread function in 2D in the maths. So it does both x and y. So it looks more like, in the world of maths, it looks like that. So it's depends how you look at it, 3D 3D thing. But I'm just doing it in 2D so I can explain it well. But it fits the 3D shape of the star on the image. So from there, it can look at the various stars in the image, and just continuing with my 2D analogy, you can have really bright stars. Here's the background. And really bright stars. Yeah. And then you might have a really dim star. And what Deifot will do is it will come along with its shape and fit the shape to the thing. So it has maybe this bright star, so it'll fit this shape here, and scale it, and then it'll be able to use that shape to count how much light is underneath it. Yeah. If it comes across something faint, so this is where PSF photometry really comes in handy, is it will take its shape, and here's the sky background, so here's the noise, that's the level of the noise, and you can see maybe it's the example I'm using is going to be this star. You can only see kind of the tip of this star, so it comes along and it goes, wow, I've still got to fit the same shape to this thing. So even though the sky background's there, I'm going to fit the entire shape to it. There we go. And so I know how much light that star should be putting out. So you see, the signal to noise for a PSFStuff image is much better because you're not kind of adding noise in. The variation is not due to how much signal to how much noise you have. It's more how well does the software think it has fitted this shape of the star to the thing it found, and that's how it estimates the error. So it is a signal to noise, and as you saw when I played around with it over here, I made some graph earlier on in the talk, which I have now gotten rid of. But you can see that the the noise here is basically sort of constant. It will get better for higher counts. So you see we've got 16,000 here and only 400 there, but the noise is only, still roughly very small, Even for something quite huge like 270,000, the noise is still quite small. So this noise is, the signal is good anyway. Hope I'm making sense. So that's why you use PSF photometry, because you can do things more accurately for fainter stars. So for brighter stars, it doesn't matter. The aperture will work just as well. But for these dimmer stars, you'll get a much more accurate image measurement, right, for this small star. So it's true that you're using a bright star in your image. Anyway, so it's not such a big deal, but it still will be better, especially if your comparison star is a bit dimmer. You want to have the best signal to noise you possibly can, and that's PSF. Another thing that is of interest, I'll go and pick out someone else's. I should leave that one open because I'll give you the grand conclusion of that soon. Someone else's stuff. That person could be me. Here I am. Okay. Do a new filter. Filter. Okay, so here we have globular cluster. See if we zoom in here. Imagine putting a circle around one of these stars and trying to measure only the light from that star. And you can actually see there's a halo because there's so many dimmer stars. It's just all merged together. So you can't do aperture photometry at all here, but you can do PSF, because PSF only just goes and finds the star, and it has the shape, so it only has to fit the shape to the star because they're all the same shape. You know what's even cooler? When you use Deify, it will come through, take the image, fit the shape of the star to the actual image, and then it will remove that star from the image and then go through it again. So it will go through this image and take all of the brightest stars out, like measure them and then subtract them from the image. Then it will go through and get the next dimmer stars and the next dimmer stars until you've just got this blank image. So you can see that's much more sophisticated process than aperture photometry. And so even down in here, in the bright center of the globular cluster, maybe not right in the center. You see, very close to the center, you can still keep on measuring stars, and that's what a couple of my students are doing at the moment. And it's easy, and you get really nice stuff, but you would not be able to do that with aperture photometry at all. So that's another benefit. Of course, you're not looking at a globular cluster, but it will help even if there's another star nearby. Actually, your field looks pretty good, so everything's pretty separate. But most of the stars in the universe are in the galactic plane, and the galactic plane, the stars are really close together, so it's usually very helpful. Now that I've opened this spontaneously, and I didn't intend to, but I'll show you what I mean. I was going to answer your Aladdin problem. So type in your thing, coordinates or whatever, press enter, and then just wait. The default that Aladdin will go to is the colored DSS thing. You will have to wait. Yep, see? So if you don't do anything, be patient, wait. It will give you the colored image. I noticed you got the black and white image. You don't have to go into that load astronomical image thing. That's black and white stuff. Just Shift Delete clears everything, and let's go Messier 15. Press enter, be patient. Play some thinking music, and there you go. So you should see colors. So next thing, this should be finished. So it's gone through, figured out where all the stars are, and it has output that here. For each file there's another file, and it's just the CSV again, where it's gone and found a comparison star in this particular file, and RL Lyrae in that particular file, and the free check stars. So that's good. For each image you have the which ones are counts and things for each of the stars. If you really wanted to do it, you could go into that spreadsheet I gave you and start manually typing them in, or we can do this. The second half of this program, called tabulate.py, is a Python program. It takes each of those files that has identified the stars in them, and it will process them all together. So it will go through and make, I'll just run it. So now what it's doing, let me just do that. It will go through each of these files and separate it out into separate files for the comparison, the RL Lyrae, star 1, star 2, star 3. So it kind of, gets them all into their own table, so you don't have to do it manually. It's done automatically for you. And you can see the benefit here. There's 1,071 images. That would take you a few weeks to do, and you'd screw it up monumentally, you see. But here, with the power of computers, it's just doing it, and it's done it in a minute or two. So it is sort of a black box in a sense, in that the student, this will just automatically do the stuff for the students, which is why I said let's do it manually as they come in with AstroImageJ, because AstroImageJ is easy to use, and use it in this sheet and see it coming out there. So you have this visual thing happening, so you can see them making the measurements, you see what's going on. But in the final swoop, once they've got the gist, let's swoop through and just use this to get the data out for them. Because the interesting thing is the analysis of the light curve and stuff like that. Once they got the idea of where this stuff's coming from, then doing this manually just becomes tedious. So here we go. And so if you look in the folder, here we have an output tabulated folder. It outputs a file a CSV file which you can open up, which is just, so here's rr the object, and then in the G filter, here's the MJD, the time, the magnitude difference, so it automatically converts into magnitude difference, and then the error in the magnitude. Yeah, pretty smooth. So if you were going to put all that together yourself, you'd be there till the end of time. You see there's 309 G images. There's 1,000 and something images all up, but they're over 5 filters. And then you have a text file which is the same, and this text file can be opened straight into Paranzo. So that's I was showing someone else something last night. So that file can be brought into this Paranzo thing, which will help them find the period. I showed you that in the other video. I don't have to show it again. It would be exactly the same file, even. So yeah, so you have all these tabulations, you have the other stars, and yeah, that's about it. So here you'll have this the data out, and you'll be able to go straight into Paranzo, figure out what the light curve looks like, and that would be great. So that is my traditional half an hour, and I mean, we could write this down. I do try to incorporate it into Our Solar Siblings materials, but the Our Solar Siblings materials get updated as I do stuff like this. This stuff's not in there at the moment, but it is sitting. Is it sitting? It should be sitting in research notes, Python scripts. Oh, no, it's not in there at the moment. So this is where I slowly start putting all of the these type of things over time as students do research, and I try to make it very simple. Oh, is that it? That looks far too old. Anyway, you shouldn't be watching this anymore. Now I'm just interested in my own stuff. Yeah, okay. My memory is getting older. It says description of, yeah. Oh no, this is an older version. We had an older file that did it, but Matthew made a better one. Yeah. Anyway, when you get around, I'll have to update that. When you get around to having all the data and stuff, and they're ready to do that automated analysis, I'll give you some more info.